Hello everyone, welcome back to the course Information Theory and Coding. In the last class, we were discussing about the Markov source model and we solved one particular problem. In the today's class, so the variations in this problem we are going to have. Okay, so for that, so let us try to consider one of the problem. So here, so they have given you the state transition diagram, and for this state transition diagram, so they asked you to find out what is h of s and what is h of s square. They have asked you to find out. So since it is a dependent source, so it is necessary for us to find out what is the initial state probability of all the state, either it is in state A or either it is in state B or whether it is in a state C, we need to find out. So let us try to read out once again the statement problem what they have given. For the first order Markov source with a source alphabet A, B, C shown in the figure, compute the probabilities of the states. So in the earlier problem, they used to give the initial state probability of being in either state A, state B or state C. Since they are not given you the state probabilities, so it is necessary for us to first find out what are the state probabilities of being in the particular state. And after that, we need to find out the entropy of the source h of s, and then we need to find out the second extension of the source h of s square we need to find out. So for that, so what is the probability of being in this state? First we need to consider. Okay, so therefore what we are going to do is, so probability of being in this state we need to consider. So the incoming branches which are appearing for each state we need to consider. So here you will be remaining in state A with emission of one particular symbol from A, and you'll be remaining in the state A only, and you will be remaining in state A where you are in state C with, and it emits a particular symbol, and you'll move to state A. So probability of being in this state will be possible only by these two branches. So the inward branches we need to consider to find out the probability of being in a particular state. So therefore you can see here the probability of being in a particular state A, it is nothing but P into P of A, means if you are there in a state A and if you emit a particular symbol with a probability P, you'll be remain in a state A. So therefore this you need to consider. And similarly, when you are in state C, if you emit a particular symbol with a probability P, you will be remains in a state A. So therefore the probability of being in a state A, it is nothing but the probability of from this state and the probability of emission of particular symbol from C to A will be therefore. So therefore the equation one we will be written as like this: the probability of being in a state A is nothing but P into P of A plus P into P of Similarly, the inward branches for the state B we need to consider. So you have a inward branches from A to B and you have a inward branches from B to B. So therefore, the probability of being in this state B, it is nothing but probability of P into P of A, probability of being in state B into P of B, we need to multiply. Similarly, for the state C, so what are the incoming branches are appearing? From B, one state it is appearing, and from C to C, one more branch, inward branch is appearing. So therefore, probability of being in state C is nothing but P into P of B plus P into P of C. So these we call it as the independent probabilities values, and based upon these probability values, it is possible for us to find out what is the probability of being in a particular state. And we also know that the sum of probability of in any one of the states, it is equal to 1. So therefore we can calculate that P of A plus P of B plus P of C is equal to 1. So by substituting this expression in the equation 1 and 2, we can arrive at an expression that the probability of emission of the particular symbol from any state, which will be given as P is equal to 1 by 2. So by using this probability values and the equation number 1, so we can calculate the probability of being in state A is nothing but 1 by 2 P of A plus 1 by 2 P of C. And since we know that P of A and P of A will be here, if I take this to the left side, so you'll be getting 1 by 2 P of A is equal to 1 by 2 P of C. So we can arrive an expression that the probability of being in state A is equal to probability of being in state C. Similarly, for the second equation, if I consider P of B is equal to 1 by 2 P of B plus 1 by 2 P of A, if I do that, so you'll be getting half P of B is equal to half P of A. That is nothing but P of A, which will be equal to P of B. So therefore, we can say that P of A is equal to P of B and P of B is equal to P of C. So therefore, if I substitute all these expression, so you'll be getting P of A is equal to P of B is equal to P of C is equal to 1 by 3. So now let us try to find out what is the probability of, that is the entropy of the each state. So when you want to find out the entropy of the each state, then what are you are supposed to do is the outgoing branches you need to consider. So this from state A, there are two outgoing branches you are going to consider. So one, this branch we call it as an incoming branch also, and this branch can be called as the outgoing branches also. So we need to consider this branch and this branch for the state A. Similarly for the state B, this branch and this outgoing branch we need to consider for the entropy. Similarly for the state C, we need to consider this branch and outgoing branch, this branch we need to consider. So if I consider those and if I find out the entropy of the first state, it is nothing but P of AA log 1 by P of AA plus P of from A to B it is going, that is P of AB, and plus P of AC, there is no symbol outgoing branches which is there, so therefore this will leads to 0. So if I substitute these probability values, so you'll be getting the entropy of the state 1, that is HA, will be given as 1 bits per symbol. Similarly for the second stage, H of B is nothing but P of BA log 1 by BA, P of BB log 1 by PB plus P of BC log of 1 by BC. Since the probability of emission of a state from B to A it is 0, so therefore we have a 0, whereas from B to B we have one symbol which is emitting 1 by 2 log of 2, but one more symbol we are emitting from the state B to state C, it will going 1 by 2 log 2. So if I substitute that, you'll be getting the entropy of the second state, that is H of B is nothing but 1 bits per symbol. Similarly for the third state, H of C is nothing but P of CA log 1 by PCA, P of PCB log of 1 by PCB, PCC log 1 by PCC. If I do that, since PCA we have one source symbol which is emitting, and from PCC one more source symbol emitting, whereas from PCB there is no symbol it has been emitted, so therefore H of C will be 1 bits per symbol. So now we need to calculate the entropy of the entire source. So it is nothing but initial probability values into multiplied by state entropy. If you do that, then you'll be getting the entropy of the source. So since you have a 3 states, that is therefore PA into HK, PB into HB plus PC into HC. Since we know that the initial state probability of all the states, it is nothing but 1 by 3 into 1 plus 1 by 3 into 1 plus 1 by 3 into 1. So therefore the entropy of the source will be given as 1 bits per symbol. And from the second extension of the expression, we know that H of S square is equal to 2 into H of S. So if I substitute that 2 into H of S is 1 bits per symbol, you'll be getting a H of S square is equal to 2 bits per symbol. So this is the one of the variant problem which will be asked in the examination. So I request all the students kindly go through this and practice more, so that you will not have any doubts when solving the problem. And there is one more type of variant. Let us try to look over this problem. So that is P14. So consider a state diagram of a Markov source of a figure. So they have given you the Markov source. So they are asked you to compute the state probabilities and find the entropy of the each state and find the entropy of the source. So whatever the problem we have solved in the earlier classes, that is this problem, similar to the same problem they have given you, only the thing is here we have a 4 states, whereas in the previous case we have only 3 states. So first, what is whether they have given an initial state probability of being in the particular states we need to calculate. Since they have not given, so it is necessary for us to calculate. So as I said you, if we want to calculate the probability of being in a particular state, then what we need to do is we need to consider incoming branches. So when you consider incoming branches for P of A, so probability of being in the state A is nothing but 0.6 into P of A, plus you can see from D to A you can come, so that is the incoming branches is appearing. So therefore probability of being in state A is nothing but 0.6 into P of A plus 0.5 into P of D. Similarly for the state B, so you can see here you'll be in the state B. From A to B you have one incoming branch, and from B to D you have a one incoming branch. Similarly for the state C, you have one incoming branch from B to C and one more incoming branch from C to C. So these are the incoming branches we need to consider in order to find out the initial state probability values. So if I use these expressions, so you'll be getting P of A is equal to 0.6 P of A plus 0.0 P of D. Similarly for the P of B, it is 0.4 P of A plus 0.5 P of D, and P of C is nothing but 0.6 P of C plus 0.5 P of B. And finally, for the third, the D state, 0.4 P of C plus 0.5 P of B. So if I use all these equations, and we also know that P of A plus P of B plus P of D plus is equal to 1. So if I use this expression and finally simplify this, so you'll be getting P of A is equal to 1.5 of P of D and P of C is equal to 1.25 of P of D. If I substitute all that expression and if I simplify that, you'll be getting P of B is equal to P of C. So by using this expression, that is the sum of initial probability which is equal to 1, if I substitute all in terms of P of D mean, then you'll be getting P of D is equal to 2 by 9 and P of B is equal to 2 by 9, and similarly for the P of A and P of C both are same, so which is equal to 1.25 into P of D, so you'll be getting 5 by 18. Then it is necessary for us to calculate the entropy of the each state. As I said you, if you want to calculate the entropy of the each state, then we need to consider the outgoing branches. So for example, if you consider this P of A. So the outgoing branches, what are the outgoing branches we need to consider is, so this is the one is the outgoing branch we need to consider, and this is one more the outgoing branch we need to consider for the source which are emitting from the state A. Similarly for the state D, you can see what are the outgoing branches we need to consider is, the outgoing branch is zero point 0.5 we need to consider and the zero point 0.5 we need to consider here. So this is the outgoing branches we need to consider. Similarly for the state C, so this is called as the incoming branch also and outgoing branch also, and this is one of the outgoing branch which is emitting from the state C. Similarly from state B, this is one of the outgoing branch we need to consider and this is one of the outgoing branch we need to consider. So by considering the outgoing branches with a probability, it is possible for us to find out the entropy of the each state. So you can see therefore HA is nothing but PAA log 1 by PAA plus PAB log 1 by P of AB plus PAC log 1 by PAC plus PAD log 1 by PAD. So if I substitute all these probability values, so you'll be getting H of A is equal to 0.97 bits per symbol. Similarly, if I calculate for H of B, you'll be getting H of B is equal to 1 bit per symbol, and for H of C, you'll be getting 0.971 bits per symbol, and for the H of D, you'll be getting 1.1 bits per symbol. So once I have calculated the entropy of the each state, then it is easy for me to calculate the entropy of the source, which is nothing but the product of initial state probabilities multiply with the entropy of each state. So if you do that, PA into HA plus PB into HB plus PC into HC plus PD into HD. So if you do that, substitute all this expression, then you'll be getting H of S is equal to 0.9839 bits per symbol. Thank you.